All right. So we're gonna go back to where we were on Friday. We were talking about directing effects and how certain types of substituents on the ring, when you're doing a reaction with an aromatic ring, certain substituents kind of dictate the outcome of the reaction, whether electrophile you're adding to the ring is going to add at the ortho or para position, or if it's going to add at the meta position. All right, so we kind of went through with one example dealing with ortho para directing, and we did it basically through resonance, right? That's all the ortho para directing observation is resonance. If you have a resonance donor attached to your ring, then it's that, and that's an atom with a lone pair that it can donate, then it's going to be an ortho para director. The only exception to that will be something like an alkyl group, which is also an ortho para director. So let me show you what I'm talking about. If I have, add a page right quick. Right, so if I have a ring like this, with an alkyl group on it, right, and I want to brominate that. So let's just do bromination. Right, that alkyl group is a donor. It's not a resonance donor, it's an inductive donor. Right, it's an inductive donor because that bond between the two carbons, the carbon-carbon bond here, is electron rich. Right, so that sigma bond is kind of it can be like an inductive donor. It's an electron rich bond. Right, so alkyl groups will act as ortho para directors. So what would the products be from this reaction? Anybody? Right, if you have this set of reagents, bromine, and then in the presence of iron bromide, what would the product of that reaction be?
So the product will have to include both of the bromines, right?
No, not both of them, but it's going to add a bromine to the ring.
Wouldn't it add a bromine to the para position?
Yes, it would, because you have a donor on the ring, but it also will add to the ortho position. So this is ortho, this is para. So those would be your two products. You would get the ortho product where bromine is here, and then you get the para product where bromine is here. And usually when you have a substituent already on the ring, the para is favored just because of sterics. All right, so as far as donors are concerned, you can have resonance donors, you can have inductive donors, but anytime there's a donor on the ring, you're gonna have ortho para directing. All right, I want to look at, I said we were gonna look at this problem right here. Because we looked at the Friedel-Crafts isolation which is adding that acyl group on. But if we took that product, let's just do another example. All right, we took that Friedel-Crafts acylation product. Let's say I brominated that. What type of effect is that acyl group going to have on the ring? Is it a donor or is it an acceptor? All right, think back to part one. Think about dipoles and polarization and all of that stuff. Is that carbonyl going to be a donor or an acceptor? Look at the atom that's attached as well, right? Because it's the carbon that's attached to the ring. All right, so is it going to be a donor? Is it going to be an acceptor? All right, all carbonyls are acceptors. Right, they can accept a pair of electrons because the dipole is here going towards oxygen. So this is partially positive, and put some electrons in there. That's partially negative. So that partially positive carbon can accept a pair of electrons because I can also draw a resonance form for that carbonyl, can I? Where I put take the pi bond and put those electrons onto oxygen. So if there's an acceptor on the ring, the acceptors are meta directors. All right, so this is ortho, that's meta, and that's para. A meta arrangement is 1-3 compared to the initial substituent. So that's 1, 2, 3, and 4. So if you have an acceptor on the ring like that, it's going to be a meta director. So your product is going to be here. You only get one product. Like that, right? Because when I do a bromination on the ring, all I'm doing is putting one bromine on that ring. All right. Questions about the meta directors. It could be carbonyl, other meta directors. If I attach like a nitrile to the ring, right? If I attach a nitro group, right? Obviously carbonyls, right? So all those would be acceptors, either by resonance or by induction. All right, so let's look at one other thing with the directing effects, and that is why we see meta directing with acceptors. Let's talk about that. And again, this goes back to resonance. If you understand resonance, how to push electrons, then this is not like esoteric to you. It's not like something mystical. But if you step through resonance, then you're gonna have a problem. All right. So let's take the same compound. All right. What would if I ask you to draw the resonance form for that, what would the first, what's the first pair of electrons you would move? Where would you start? All right, when you looking to do resonance, you always look for the same pattern, donor and acceptor, adjacent to one another. All right, so you have that pattern here. All right, so I'm going to start there, and then I'll let you help me around the ring. So if I push this pair of electrons here, like that, the resonance form should look like this. Hopefully you'll see this right away, why acceptors are meta directors. Right? And then I broke that pi bond, so I have a plus charge on this carbon. What position is that plus charge in?
Meta.
Look again.
Ortho.
It's in the ortho position, right? So that means that the ortho position, if I'm doing, let me go back a little bit. We're doing electrophilic aromatic substitution, right? So we're adding, yes.
I have a question.
Go ahead.
So it's not exactly the point where you said the ortho site was. So if it's like before the para, then it's still considered ortho because it's in that region.
It is ortho because I have a substituent on the ring right here. So that's number one, okay. Right? So automatically that becomes position one, and everything else is relative to that. So that's 2, 3, 4, 5, and 6, like that, right? So this is still 1, and that's 2, 3, 4, 5, and 6. All right, so the ortho is actually deactivated. And you can see that, right? If you're adding an electrophile, you need electrons. You can't add an electrophile to a carbon with a positive charge. You need some electrons there. But you just took the electrons away from the ortho position, right? Through resonance. So that when you put an acceptor on the ring, it deactivates the ortho position, right? And then we draw the next resonance form, which will be here. Right here, that's positive now. Is that right? Is that the right resonance form?
Yes.
Where's the plus charge now?
On the pair.
It's at the para position. So that's also deactivated. Right, so anytime you put an acceptor on the ring, it's going to do, this is what's going to happen. It's going to deactivate both ortho and para. But if you notice, in both cases, you got a pi bond here at 3, that where a pair of electrons can be used. And here you still have that same, not the same pi bond, but you also have pi bond at 3 in the second resonance structure. So the meta position is activated, but the ortho and para positions are deactivated. All right, so that's why we put an acceptor on the ring. It acts as a meta director. When you put a donor on the ring, we already saw that up top. It acts as an ortho para director. All right, any questions about that? About the directing effects?
I have a question.
Go ahead.
So on the last problem you did,
Mhm.
the addition that you added, the carbonyl, was that
This one right here?
the substrate?
Yes.
Okay.
You're talking about this one in purple?
Yes.
So the carbonyl is a substituent on the ring, but it's the ring that's doing the reaction, right? And since the carbonyl is an acceptor, which we just showed down here, right? You can give a pair of electrons to it, to that carbonyl carbon, and do resonance with it. So since it's an acceptor, it's going to be a meta director. That's why the bromine ends up here, right? Because that is 1, 2, 3. It's at the 3 position or the meta position.
Okay.
All right. Any other questions about the directing effects? If you go up to, let's go back up here on that handout. And I got a couple of problems on here. Well, they're already done, right? So you can see right here, this is just an example up top where you have a methoxy group, which is a donor, right? A great donor on the ring, and that's going to give you ortho-para products. And then you have a nitro group on the ring, which is a great acceptor. And that's going to same reaction of bromination. You're going to get meta products. All right. And again, this is dealing with dye-substituted, when you making dye-substituted products, right? Because you got 2 groups attached, so it's dye-substituted. Up here is just the positions, right? This is a mono-substituted ring, and in a minute I put on a second substituent, I start using this convention, this ortho meta para convention, like 1, 2, 1, 3, or 1, 4. Right? All right. Any other questions about the ortho para directing, about any of the reactions, anything? I think we can work through a couple of these problems at the bottom, and we'll actually be done. Might even stop early rather than starting a new section, because the next section is kind of, well, if you had part 1 lab, then it'll be familiar to you, because the next section is dealing with spectroscopy and NMR. All right, so let's take the first 2 problems and let's work through those. We're just predicting the products because we've already seen those mechanisms. And then for the third problem, we're gonna walk through it step by step. And then I'm gonna add a little twist to this. And then we're gonna work one more problem, and then we're gonna stop. Because Monday, I could feel Monday coming through Zoom. Like I feel that Monday vibe. So can somebody draw in what the product of that first reaction will be and tell me what type of reaction it is? Is it an alkylation? Is it an acylation? Is it a halogenation?
It's an acylation.
Acylation, good. I'm just gonna put in, let me fix that C, it looks like an R. right? It's acylation. What would the product be? Can you annotate the screen, or you just want to tell me? Right, we know this is a part of the product. Is that right?
Right.
Would it be the same thing, but you just drop in CL?
Say that again, though.
Would it be the same thing, but you just drop in CL? Or am I far off?
Yeah, so the chlorine is no longer going to be I think I understand what you're saying, but I want to make sure that I'm understanding it properly. What do you mean by dropping off CL?
Like the CL is gonna take it out the product. So I think it'll end up being AlCl4.
Mm-hmm.
So it'll be that ring, and then the second reactant the same, but just no Cl because it'll be AlCl4.
Okay, but if we're acylating the aromatic ring, right? We're trying to add this piece to it.
So would that attach to where CL's at?
Yes, so that you would replace. This is a shortcut way of thinking about it. Even if you don't know the mechanism, you can predict the product. You would replace the chlorine with the aromatic ring, right? That's the bare bones concept. So the acylation part is going to happen. Sorry about that. Here, right? You following or no? And then plus, we'll say HCl plus AlCl3, because that catalyst is always going to get regenerated. Anybody not see that?
It's an H on the Cl because it's always hydrogens on the ring, right?
Yeah. So let me go back to the mechanism up top, and I'll show you where that came from. I'll do this one because this is clearer, right? So there's a hydrogen wherever you add your group to, right? There's one hydrogen on every carbon in that ring. So the HCl will come from this part, right? Where the hydrogen here is going to get snapped off by the catalyst, right? Or the catalyst after it's been brominated or chlorinated in the case of the Friedel-Crafts acylation, right? So that's where the HCl is coming from, because of part of that mechanism. Actually, let me just go because we did an acylation down here. Part of the mechanism is you always start with an acid chloride, but part of the mechanism is the catalyst becoming negative, right? You see over here, by pulling off the chlorine from the acid chloride. And then at the end of the reaction, when you get ready to reestablish the aromaticity, that same anion is going to come in and act as a base and pull that hydrogen off so you can do your elimination and put your double bond back. So that's where the HCl is coming from. And then you always come back to that same catalyst, right? You never use it up. All right, did that answer it?
Yeah, so the catalyst can be altered. Like,
yeah.
Okay.
It can be altered throughout the course of the reaction, but at the end, it's always going to be reformed.
Yeah, I was just trying to figure out like why not put the Cl on the ACl3 and just make it AlCl4.
Well, you can, right? But that's not the final step in the mechanism. That's the first step in the mechanism. You see up top where you activate the electrophile in step 1. So that does happen, but at the end, you always go back to your catalyst. You always regenerate it somehow. And the way it's regenerated in this case is through proton transfer. to that anion so that one of those chlorines ends up with that proton and it becomes HCl, and then you get AlCl3 back. So yeah, you're right. It does get altered, and it does get it does change, right? It becomes an anion, it becomes tetracoordinate, but at the end of the day, it's always going to come back to the original form of itself.
Okay. Can you scroll down a bit?
Yeah, I'm going back to the problem we're doing. All right. So that acylation, what you're trying to do is acylate. You want to add wherever that carbonyl is, that's the carbon that you're going to add to the ring right here. All right, nothing else. So the chlorine can't come. It's just the carbonyl. All right. What about the second question? What type of reaction is that?
Bromination.
It's a bromination. What's the outcome?
You're gonna basically just add a bromine to that aromatic ring, and then it'll form HBr and FeBr3.
Here's your aromatic ring. I'm just gonna add a bromine, like you said, and then plus HBr, and then plus the catalyst, regenerated. Always regenerated. Doesn't get used up. If it gets used up, it's not a catalyst, it's a reactant.
Dr. Russell,
Yes.
I know you probably said it already, but just for clarification, how you know exactly where the bromine is supposed to be placed? Like, how you know?
It doesn't matter here because the ring is not substituted. You can put it anywhere.
Okay, but for cases when it does matter, like, how would you know which side to put it at, like the ortho, the para?
Yeah, so that's going to depend on what's on the ring, whether there's a donor on the ring or an acceptor on the ring. That's going to determine where your electrophile ends up. If there's no substituents on the ring, then it doesn't matter, right? It can be electrophile can be on any one of those 6 carbons. But the minute you put a donor on the ring or an acceptor, then it's either going to be ortho-para direction or meta direction. So that's how you distinguish between it. If it's unsubstituted, it doesn't matter where you put the electrophile. If it's substituted, then you have to ask whether the substituent is a donor or an acceptor, and that'll determine the outcome of the reaction. So like if I took the product and from the second reaction that had bromine on it, and I want to do another reaction on it, what is bromine? Is it a donor or an acceptor?
A donor.
It's a donor. So if I did a reaction on that product, then any electrophile I add has to come in either ortho or para. What if I took the top structure and did another reaction on that? What do you think? Is that a ortho-para or is it a meta-directed?
Meta.
It's a meta-directed. So anything I added to that top, if I did another reaction on that ring and I added something to that, then it would have to come in at the meta position. So any further reaction on the product is going to be determined by the substituent that's on the ring. All right. Now, the last problem, we haven't done that mechanism for that, so we're going to do that now. All right. This is what we call a Friedel-Crafts alkylation. It's a Friedel-Crafts alkylation. That means that I'm adding an alkyl group to the ring, and the alkyl group again is the electrophile because we're doing electrophilic aromatic substitution, meaning I'm adding an electrophile to the ring and substituting one of the hydrogens on the ring, right? So let's see if we could just predict the product. What do you think? What are you looking for when you're doing this electrophilic aromatic substitution. Well, you know your ring is going to be the nucleophile, and whatever this start material is here, what I'm looking for is what a leaving group is, right? Because this is all stuff we've done before. So I'm looking for the leaving group, which in this case is chlorine. And it's at that carbon right here. That's the carbon that the ring is gonna attack. Are y'all following that? It's just a quick and dirty way to think about it. So if you just have to predict the products and not put the arrows in and go through the mechanism, then you can know that right away. That's gonna add to the ring, that carbon where the chlorine is. All right, so what do you get? What's the product from that?
Would you just attach all of that to the ring besides the chlorine part?
All of it. All of it. Everything except the chlorine. You're exactly right. Let me fix my ring. It's sloppy. All right, so I'm going to attach that group to the ring just like that. And then, of course, the side products will be HCl, which we don't really care about. And we get the catalyst back, right? We don't care about the side products more so than we do the main product.
Doctor,
All right, go ahead.
so for the second ring that you drew, is that 3 carbons attached to the little branch?
Yeah, you see right here how in the, let me see if I can, you got you have this carbon right here, is that right? And 3 carbons attached to it.
Oh, okay, I get what you're saying.
Yeah, so it's the same carbon over here. It's the geometry just looks a little bit different.
Okay.
Mm-hmm. But it's that carbon where chlorine is that the ring is going to attack. Let's go through. Let's see if we can walk through the mechanism. Just walk it down. What's the first step? It doesn't change, right? So if you know the mechanism for acylation or halogenation, it's the same mechanism, the same process, just different substrates. So what's the first step in these mechanisms?
Electrophilic activation.
Right, so we're gonna activate our electrophile, good. Right, normally the way that happens is the catalyst is gonna form some type of complex with the electrophile and remove the halogen from it, right? Or remove the leaving group. So in this case, this is my starting material. All right, and I'm going to react that. In this case, it was iron 3 chloride, right? So it's going to form a complex with this. And then we rip off that chlorine, is that right? So you're going to end up with a tertiary carbocation plus iron tetrachloride, and it's negative. Uh-oh. Is that right?
Yes.
Yeah, so that complexation part is important. That's the purpose of the catalyst, is to make that complex so that you can get a really highly reactive electrophile, right? And then in step 2, what's the next step?
Nucleophile attacks.
All right, so the ring is gonna be the nucleophile, and let me erase that. So it's not a radical. The ring is gonna attack that carbocation. Come on, Russell, get your mind right. And erased everything. So now this is going to attack here, is that right? And the carbocation is my electrophile, Again, it's electrophilic aromatic substitution. I'm adding an electrophile to the ring. The carbocation is my electrophile. And once I attack it, sorry. I have now this group attached to the ring and a positive charge on that carbon. Is that right?
Yeah.
I have a hydrogen here, right? And that hydrogen up there, that's what I'm going to use to do the elimination in the final step. Let me fix this tert-butyl group because that's sloppy. Wrong color, Russell. Get it together. All right. That's a little better. All right. And then in the third step, what happens?
You reestablish the aromaticity.
Reestablish aromaticity. Doesn't change. Just all the other reactions we looked at was the same, right? You went through an activation and then a nucleophilic attack and then reestablish aromaticity because you don't want to break that aromaticity up because it's energetically, it's just too unfavorable to do that. Remember when we first started talking about benzene, we were saying how perfect it was. Like all the bonds are the same length, everything is perfect. So you don't want to break that up because you lose a lot of energy by doing that. So you always reestablish aromaticity at the end. To be honest, that's probably what drives the reaction, trying to get back to normal. Right, so, and it's that anionic iron that's gonna come in, boom, take this proton and eliminate. Right, and that's gonna give you back your aromatic ring, which looks like this. Still, nothing has changed from that. And then boom, your substituent plus HCl plus the catalyst regenerated. All right. So when you do the acylation, the alkylation, the bromination, all of those reactions are going to follow a similar pathway, right? Mechanistically. I'm struggling with this tert-butyl. I'm gonna get it though. All right. So they all follow the same or similar pathway. What if I took that product and I wanted to do another substitution reaction with it, or aromatic substitution? Would that alkyl group be a meta director or orthopara director?
Orthopara?
It's orthopara. All alkyl groups are donors, right? They are, but not through resonance, through induction. All right. All right, so if I took that and did another reaction on it, that group is going to be an orthopara director. So any electrophile that I add to that ring, that substituted ring, is going to add at the ortho position or the para position. All right. I want to leave it here. But one of the problems with the Friedel-Crafts alkylation is that if you do it on a primary carbon, it won't give you the product that you expect, right? Sometimes you would have like a rearrangement or something like that happen to where it just doesn't work, right? It's not going to ever give you that product where that primary carbon is substituted or that primary carbon is your electrophile. So what do you think about this? Can somebody tell me in the electrophile activation step, let's just look at that, right? Because the expected product should be this. right? Your ring is here. I'm just gonna abbreviate that, and then it's 1, 2. Your expected product will be that, right? Where that primary carbon right there is just attacked by the ring, right? After you activate it. But in the activation step, what would that look like? Anybody? Would it be any different from the other activation steps? What's the normal process for activating that electrophile? What do you form with the catalyst? When you form a complex with the catalyst? Is that right? Try to do that. Right, when you form this complex, what would the cation look like from the formation of that complex? Where would it be? Would you give me that?
Oh yeah.
Mm-hmm. What type of carbocation is that? Is it primary? Is it secondary? Is it tertiary?
Primary.
It's primary. What do you know up to this point? We've seen this more than once now, on many occasions. It's if you have a primary carbocation and you have a tertiary carbon close to it, what do you know? What could happen? There's a type of rearrangement that can happen. And we looked at this when I think we did the E1 elimination. We talked about it too. What rearrangement can happen here to give you a more stable carbocation?
Is it a methyl shift?
Well, you could do a methyl shift is one of the rearrangements. That's true. But if you look at the product right here, you can see that it's this carbon right here that got substituted. So I could do a methyl shift. That's true. But then that wouldn't help me, because if I did a methyl shift, then I would just secondary carbocation right here.
Oh, right.
Right? You following?
Mm-hmm.
And then I'll just end up with a secondary carbocation, which is not, I mean, it's not horrible. But there's another thing that I can do too, which is a hydride shift, right?
Mm-hmm.
So if I move the hydride over to here, then that's going to give me a tertiary carbocation. And that will be my electrophile. So one of the drawbacks of Friedel-Crafts alkylation is actually rearrangement of your carbocations, right? So that would be the hydrogen that I move would end up here. Keep in mind there are already 2 hydrogens on that carbon. So this would be it will be a 1,3 hydride shift. Right. A lot of times when you have primary carbocations, they're gonna rearrange some kind of way. It's either gonna be a hydride shift or a methyl shift, but something has to happen in order to stabilize that primary carbocation. That is not a good, that's not a good carbocation. And then you can see right here in the product that this is the electrophile that got added to the ring, not the initial primary. All right, and any questions about that? If you go through the second and third step in the mechanism there, you can see that. But I think we've exhausted, well, we haven't exhausted, but I think we're at a good place right now to stop. Because I don't want to overwhelm you, and then you still got to take the exam. So we're gonna stop right here, unless you got questions. Go ahead.
Can you go up a little bit? More, like the last page.
This page right here.
Yes. Okay, I see it. Oh, and Dr. Russell, for the exam, is it just covering like what we did, like stopping Friday, or today's lecture as well?
Well, it's not really. Well, we've been talking about this electrophilic substitution from, I think, Wednesday, Friday, and today. So it's all together.
Okay, and I can't access the what is it? I can't access one of the worksheets from the, I think it's the benzene and aromaticity section, because I submitted it already. So I need to see it so I can get the worksheet that we worked on today.
Okay, if you get the if you go into Blackboard in the course notes folder, you could just download the notes, because that worksheet is in the notes. It's the very first page, as a matter of fact.
Okay, but then you say you were gonna like add a second attempt to the assignment.
Yeah, I will, to the conjugated stuff. Yeah, I will.
Okay.
So you're saying you turned both of them in already?
Yes.
Okay, I'll just reset them both.
All right. And when is the test close?
Wednesday. It'll
All right.
open today. It'll be open until Wednesday. I didn't do lockdown because I don't know how that's going to work, and I didn't have a chance to investigate it. So it's just 2 parts. It's a multiple choice part and a written part. But everything is due by Wednesday. So you don't have to wait until the end. You can finish it whenever you get a chance. But it's all and it's you get 2.5 hours on the multiple choice part. All right. Any other questions?
No more questions for me, but have a nice day.
All right, do the same. Anybody else have any questions?